Another specific example of random variables, or specifically continuous random variables, is the normal distribution. So we've already done one specific example for discrete, which is binomial, and now we're looking at a specific example for continuous random variables, which is normal distribution. This is a very typical type of distribution that is studied, and it's something that explains the behavior of naturally occurring things. So we're going to look at all the ways to calculate and properties of normal distribution. And then there's another lesson on standardization. We're looking into these two graphs. So these are graphs of normal distribution. So they have this normal behavior, this normal bell curve or a Gaussian curve. And you can see that the curve changes based on the standard deviation of the function. So the smaller the standard deviation, the more concentrated the data is, the larger the standard deviation, the more spread out. Another nice visualization is this. If they've taken the measurements for the right-hand span of females and the right-hand span of males, you can notice that if I take the graphs separately, they follow a normal distribution, obviously with some peaks, but generally we have a normal distribution. If I take more and more measurements, it's going to be even a smoother curve. So normal distribution is a naturally occurring event in real world, things like height, weight, lengths of leaves, test scores, for example. If everything is normal, there's nothing skewed, they follow normal distribution and they satisfy certain conditions. Now, remember, normal distribution is an example of continuous random variables, which means there's a PDF, there's a probability density function that explains the function itself. This is the PDF for normal distribution. However, a big disclaimer, you are not expected to compute it. You're not expected to use this formula. It's just for formality to show you where the formula is from. So we will use the calculator mainly to calculate the normal distribution. So if x follows a normal distribution, it relies on two main things. So the binomial relied on the number of trials and probability of success. In normal distribution, we rely on the mean and the standard deviation to help us explain the distribution. So if I say that something follows a normal distribution, if x follows a normal distribution, I will write it as the mean and the standard deviation. Now, careful, I'm saying standard deviation, but the notation here is the variance because that's the notation. But when we do calculations, we use the standard deviation. So for example, if x follows a normal distribution of 4, 2 squared, this is how they'd write it. It means the standard deviation is 2 and the variance is 4. If you are seeing normal distribution of 4 and 2 only, it means that the variance is 2 and the standard deviation is the square root of 2. So they have to write it as the standard deviation here. How does the graph look like? Well, the center of the graph exactly here at the peak is the mean. It's also the mode, it's also the median. So this exact value represents the mean, the mode, and the median. All together, they're quite at the center. That's why it's normally distributed. You can see that as you move away from the mean, I can nicely calculate, I can say that some of the data is 1 standard deviation away from the mean, 2 standard deviations away from the mean, 3 standard deviations away from the mean, and then the tails eventually die out in here. So there's no limit, there's no end to it. We say it goes from negative infinity to infinity. Again, back to the definition of continuous random variables. But we know that eventually, as you go very low here, the probability is quite small. So we don't say it's 0, we just assume it's very small. 68% of the data lies within the first standard deviation, and then we'll talk about the other calculations also. So these are the features. You can pause and read through it. I'll just quickly explain some important parts for these. So it's a bell curve, it's symmetrical about the vertical line x equals to mu, and the maximum value occurs at mu exactly Points of inflection, this is related to calculus. So if you've done calculus, you can see that this will be considered a point of inflection here, where the concave of the function changes. The curve depends on the mean and the standard deviation, as we've seen in the beginning. And the probability is given as the area under the curve. However, we will not use integrals here. We will use a built-in function in the calculator to help us compute normal distribution. The area below the curve is 1. The domain is from negative infinity to infinity. If the area of the curve is 1, and if the mean is at the center, it means half of the data here. The probability below the mean is 0.5, and the probability above the mean is 0.5. So there are some standard percentages that you will need to know, because if it shows up on a paper one, you're expected to use these standard percentages. So within one standard deviation, you have 60% of the data. Within 2 standard deviations, 95% of the data is in there. And within 3 standard deviations, 99.7% of the data is in there. And then right at the tails, you have the very end. We just assume there's a very small percentage of the data still in there. So this is how we compute them, and you would know, obviously, less than would be 0.5, and more than the mean will be 0.5, or 5%, 50%, 50%. Now, using the GGC, it's the same place in distribution, and it's the first 3 that we will use. Actually, we won't use the first one as often. The default every time you go into normal distribution is always going to be 0 and 1. So if I go here, you'll see the default is 0 and 1 for the mean and standard deviation. We'll talk about that when we do standardization. Keep in mind that continuous random variables can never be exactly a value, so I will never benefit from the normal PDF here, because you can never be exactly 64. We talked about that when we did continuous random variables, which also means that if I'm looking for x bigger than or equal to 64, is the same thing as saying x is bigger than 64. Now, when do we use each one? We will use PDF usually is if you want to graph the curve. You'll never see me use it in here, but in case you want to graph the curve, I can do normal PDF with X value. Let's keep this as the mean, and I'll do a zoom standard. I can graph this if I want to. I'll just change the window to probabilities are small, so we're just gonna go with 2 and you can see the bell curve happening. The mean is at 0 and the standard deviation is 1, so that's how it's moving here. So the first function is just if you want to graph it. We will use normal CDF. This is the cumulative distribution function. So if I'm looking at the probability of x being less than or bigger than, this is what I use. What it takes in is it asks you for the lower bound, what's the lowest value, upper bound, the mean, and standard deviation. If your lower bound is a negative infinity or a positive infinity, we tend to write them as very big numbers. One way to write the big number, positive infinity, is to say 1e99, or 1 times 10 to the power of 99, and negative infinity would be negative 1e99. So you'd go 1, and then e is here, and then 99. So this would be an equivalence to infinity. We use inverse norm if you are given the probability and you need to find the value that gives you that probability. So we use the inverse norm function to help us find that. It takes in the probability you have, the mean, and the standard deviation. So how to approach questions in an exam? If they rarely show up in paper one, but if they do, you're expected to use the information that's given or the standard percentages that I explained on the previous slide. I'll show you how to use them if needed, but typically we expect you to use the calculator if it's available. If you are using a calculator, obviously you don't want to write a normal CDF and then write the parameters in there. That's not the best show of method. Another way you can show your method is by doing a small sketch. So if you're looking for the probability of x bigger than or equal to 3, where x follows a normal distribution with a mean of 4 and standard deviation of 2, I'll just do the sketch. I'll show the mean, and I'll show where 3 is, and I will shade the area that I'm looking for. I'm looking for the area below the curve that's above 3. So this is the area I'm looking at. This is enough to show you're working, and then do the computing on your calculator and write the answer. Recall expected values because we're going to use that. So the expected value in a normal distribution is just the number of trials you have multiplied by the probability. So again, we've done these in probability questions also. We're going to go through a full worked example. This worked example will cover everything typically asked about in normal distribution. So I would encourage you to pause, look through them. I'll quickly explain through the answers and how the calculator is used also in each one. So the first one asks for a sketch. Notice how everything was converted to seconds because you are dealing with the standard deviation is in seconds and so on. So the x follows a normal distribution of 90 and standard deviation of 20. And this would be the sketch. So I'm just showing how it slowly falls below as I'm getting to these values. So this would be the 90, this would be 110, 130, 150, and so on. So 70, 50, 30. Now, if I want the probability that a person waits longer than 2 minutes and 10 seconds, so you are looking for x bigger than 130. Now, 130 is not a coincidental number. It's here. It's exactly more than 2 standard deviations. So how would you show your work? You would shade this area, and then you will start doing the normal CDF if you want to. If it's a non-calculated paper, then you use the standard value. So if I'm looking for more than 2 standard deviations, so it means I'm looking for this area. It means I can find these values and just do 1 minus these values. So it's just about it's like blocks, just matching the blocks up and subtracting things. So I can find this part by looking at the fact that this is 95%. So I will take half of 95% to know what this is, and add it to the fact that this is 50%. So 50% plus half of 95% will give me all of this area. And then I can do 1 minus that to give me the upper area here. Remember, things are symmetrical. So if I'm looking for this area, it's equivalent to looking at this area. Just to keep in mind. So I will do 100% minus the 50% and half of the 95%, which is 2.5%, which is 0.025. Now, if I use a calculator from the shading, the calculator will ask you what is your lower bound. So distribution, CDF, it will say what is your lower bound, what is the upper bound, what is the mean, what is the standard deviation. Lower bound and upper bound depends on your sketching. That's why it helps when you sketch. So lower bound will be the beginning of your sketch, which is 130. The upper bound would be infinity. So I will write 1 times 10 to the power of 99. Then I'll put my mean and then standard deviation. I compute it. It's going to be 0.02275. Now, it's slightly different from the answer found here, but this is because these are approximate values. They're not accurate. This is a bit more accurate. So on a paper 2 test, you are expected to use the calculator. Do not use the given percentages. Then it says find the probability a person waits less than 1 minute and 10 seconds. So that would be the probability of less than 70. Same idea. I'll try to use the approximate. I'll try to use the exact percentages. So I know that the area within 1 standard deviation is 68. So I'm going to take half of that. And then 50 minus that will give me the less than, which is 0.16. And then if I use the calculator, my shading tells me that my lower bound, I'm shading all the way down. So my lower bound is negative infinity. My upper bound is 70. And then with the mean and standard deviation, I get 0.16 also if I round it up. What if I'm looking at in-between values? So what if I want the probability between 68 and 95? So I'll just shade the area, noticing that I go beyond the mean here. My lower bound this time is 68, my upper bound is 95. Remember, it doesn't matter if there's an equal to or not equal to, you will still type in the same answer. So don't type in 69 in case, or in here, type in 64 because this is a strictly less than. In continuous random variables, it doesn't matter whether the inequality is strict or equal to. So the normal CDF is going to be from 68 to 95, and then that will be the answer. Pay attention to the questions. If they say find the percentage, then you need to just multiply this by 100. Now, what if I know the reverse? What if I know the area? This is where inverse norm comes into play. So if I know that 31% of people waited less than t seconds, find the value of t. So this is what you're looking at. This time I know what the output is. It helps to know, sketch it somewhere here. So you know 0.31 is less than 50%. So you know that t is going to be somewhere below 90 here. So I'm just going to assume it's on a random place here, and I'm going to shade below. Somewhere here, I don't know where it is, but this area is going to be equivalent to 0.31. Then we go to inverse norm. We go to inverse norm, which is the third one. And I will type the area that I know. I know it's 0.31. My mean is 90. My standard deviation is 20. And I'm shading to the left. The tail of my shading, or the ends of my shading, is to the left. And so I will shade to the left, and it's going to give me 80.08. Or if I simplify this, it's going to give me 1 minute and 20 seconds approximately. So exactly at 80 minutes here, and 1 minute and 20 seconds, the probability less than that is 0.31. And you can check your answer by substituting in. Now, for older calculators, you will not have the tail option. The default tail is a left tail. So what happens if I'm shading more than? It is known that 23% of the people waited more than t seconds. So if I'm waiting more than t seconds, 0.23, again, where am I here? If I'm more than, it means my shading is to the right, but my shading is not more than 0.5. So I have, if it's more than 0.5, it means I'm crossing the mean boundary. So I'm somewhere here shading. Or exactly at that t value, so this is my t value here somewhere, more than would be 0.23, but remember the area below the curve. The area below the curve is always 1. So if I'm shading more than if the shading more than is giving me 0.23, it means the shading less than is 0.77 at the same exact t value. So remember, it's symmetrical. So more than t is 0.23 and less than t will be 0.77. So you can use either definitions to help you compute the t value. So this is my shading 0.23. So I can use 0.23, 90, 20, but this time my shading is to the right. My tail is to the right, and I can compute the value. So notice when it's to the right, I get 104.7769. Alternatively, if your calculator doesn't have those options, or if you don't want to switch the tails, you always want to keep it to left tail, I could do the less than and just take 1 minus the 0.23. So the area less than t is 0.77, and then pick a left tail. In this case, if I pick a left tail and I do the area 1 minus, I get the exact same answer, which is 105 seconds, which is 1 minute and 45 seconds. All right, now we get to other questions. For example, there are 200 people observed and the length of time they waited is noted. Calculate the number of people expected to wait less than 50 seconds for the elevator. So expected value is always the number of trials times the probability. So find the probability first, which is, in this case, when I compute it, it will give me 0.025. This is if you're using the given percentages, which is 5 people. Because we'll just take the answer from part B, sorry, not part A. And from the calculator, I can find the probability of 50, which is 0.2275, and then I'll just do the expected value as usual, 200 times that probability, which will give me 4.56. So that's approximately 5 people. So you've noticed there was a center option in the inverse norm here in the center. So when do we use that? So we're done with this question, but we're starting another question just to explain the center. This is an example where the center is used. The weights of the apples falls in normal distribution, and they're rejected if they fall in the central 80% of the distribution. So if we do the normal distribution with a mean of 45, if they fall within 80% of the center, so the area is 0.8, then we reject the apples. So find the value of the limits where this will lie, and this is where you use the calculator for that. So we do inverse norm, the area 0.8, mean, standard deviation, but this time we select center. And what the calculator will do, it will give you the lower boundary, so the lower limit, and the upper limit. So the area between those two values is 80%. So these two are the answers to the question. You can practice these questions on normal distribution. I've tried to cover everything related to it in this video. So make sure you practice these. And then next lesson, we'll talk about standardization.